Any reaction that involves a transfer of electrons from one unit to another. Okay. So when we looked at this example on whatever it was, what was that day? Thursday? We referenced the calcium. So let's take a closer look at the calcium. What is the charge on that calcium atom? Nothing. Okay. So we saw in the upper right-hand corner it is 0. Okay. There's nothing written there, so its charge is 0. If we look at the calcium in the product, this is where things become a bit weird. Because we've been referring to the charge on calcium, but is the charge on calcium explicitly stated in that formula? No. Okay. It's implicitly stated because we have to take a look at the charge on the compound, which, as Alexander is suggesting, is 0, because there's nothing written in the upper right-hand corner, and we have to dissect that down into the charges of the individual species that make it up. Okay. Hydroxide is what charge? A -1. With 2 hydroxide, it's present. What does the charge then on the calcium have to become? A +2. Okay, and this becomes important because what's happening is that the quote-unquote charge on our calcium has changed. Okay? How does it change from a 0 to a +2? We'll address oxidation. Still, we've got to address why it's changing or how it's changing. Okay. Sharing of electrons. But if it's sharing electrons, does it still have them? Yeah. Okay. Why? What's happening here? It's more than just sharing. It's a full-on switch. It's a trade-off. Calcium started at the beginning with its electrons, and during the course of this reaction, it said, "Here, hydroxide, take them. You get to own those," and that's how the OH became negatively charged. Okay? So somehow or another, calcium is straight up just ditching 2 electrons. Okay? How do we know it's electrons and not neutrons?
Because you can't pull neutrons out of the center of an atom.
There's another reason. What happens if I change the neutrons? I change the mass of the element. Does that have anything to do with the charge? No. Okay, so I could change the neutrons. That's not going to show up in how my equation is formatted because nowhere in there do I account for the number of neutrons. Okay, so changing the neutrons does nothing to establish the charge. Couldn't I have added 2 protons? Wouldn't that make it a +2?
Again, same issue of pulling something out of the nucleus of an atom.
I'm not removing it. I'm adding 2 electrons, 2 protons. It's changing the identity of the element. So back when we went through and looked at our subatomic particles, I said you needed to know what they meant. Okay? Protons define the element. If we change the number of protons, we don't have that element anymore. The symbol changes. Since the symbol is the same, can we have changed the protons? No. So what did we have to have changed? Can't be the neutrons, can't be the protons. The only thing left is our electrons. Okay? And now we run into this issue of what's happening here, because we started to call this charge. And I would argue it is not charge. Okay? What we're looking at is the oxidation state. The oxidation state is the balance of electrons and protons within an atom. The charge is the balance of electrons and protons in a unit. Both of them are saying electrons and protons. So they're both the same thing, and yet we use them in inherently different processes. Okay? So it is very easy to get them confused. What we have to do is make sure that we separate that out. Okay? When we're looking at our reduction and oxidation reactions, what we are looking at is not the charge, but the oxidation state. Okay? So, what can we do with it? Well, we need to be able to identify them. So our charge is always, always, always given to us because it is the number written in the upper right-hand corner every single time. Okay? The oxidation state, I would argue, is something that you always have to calculate. Okay? And there are rules on determining what the oxidation state are. For the 5, I think it actually may be 2 or 3 people that watched the oxidation state video, okay, there was really only one rule that I said needed to be memorized. What was that one rule? Cool. Oxygen, did I spell that right?
Yes.
Oxygen has a -2 oxidation state. Right? That is the one rule we need. Because everything else, as far as the rules on our oxidation state, are things we've already done and already used. Okay? So let's go through and take a look at our charges. What is the charge on the first unit now boxed in? 0. What is the charge on the next unit? What is the charge on the next unit? What is the charge on the nitrogen in that unit?
We don't know.
It is an invalid question. Okay. Why is it an invalid question? The charge applies to the unit, not the pieces of the unit, but the entire unit. Do we have nitrogen as a unit? No. That question doesn't work. Okay. How could I change that question so I can start to apply the balance of electrons and protons on the nitrogen? What is the oxidation state on nitrogen, the element in that unit? Why is that so different from the first ones? Well, what was the first unit?
It was a lone element.
It was a single element, which means the balance of protons and electrons in the unit is the exact same as the balance of protons in the element. I get the same answer for oxidation state and charge. Same deal for the second one. As soon as I move to the third and the fourth one, now things go haywire. And I can't apply charge to the individual elements within it because the charge applies to the unit.
Is there a formula for it?
For which?
For compounds that have, what if you want to find a separate charge from the compound to an individual element?
So what did we say about finding the charge on the element in a compound?
It's invalid.
It's invalid. So we will never find the charge. There is no formula. It doesn't exist. Because we will never find the charge on that element. What will we find?
I have no clue.
Oxidation state.
The oxidation state. Is there a formula? Yes. And ultimately that formula is looking at the balance of protons and electrons within your individual system. Okay. So let's go through and solve that tricky formula for that first system. I want to know the oxidation state for that first unit. Just copper. How do I solve this? The number of the element. How many of that element show up in that unit? Okay. The oxidation state I have to solve for, which means it is X. This has to then, or then I would add the next element. Well, what's the next element? There isn't one, so I'm just adding 0. So really I just have 1 times X. What does this have to equal? Has to equal the charge. And we get this stupid word reformatting issue sliding that charge down, but that equals your charge. What is the charge on that unit? 0. Which means the oxidation state must be 0. The charge and the oxidation state end up being the same thing. What do you expect the oxidation state for the next one to be?
2.
You'll find out it's positive 2. What is the oxidation state for the next one?
To calculate that.
It's also a bad question. What's wrong with that question? I need to specify the element. The oxidation state applies to the element. The next one, what next one? Nitrate? That's NO3. That has nitrogen and oxygen. Which one am I asking about? Okay, so let's start with the easy question. The oxidation state for the oxygen. -2. How do you know that? That's the one rule you have to memorize on your oxidation states. Okay. How do we determine the oxidation state on the nitrogen? We go through and deal with that formula. The number of our first element. How many nitrogens are there?
1.
What's the oxidation state? Plus the number of the next element. 3. Its oxidation state, so it's pause on the -2. You're going to tell me it's y because we have to solve for it. Okay. This has to equal what? Why is it now -1? When we did nomenclature, it was always freaking 0. Why are we switching?
Because the compound.
Upper right-hand corner.
Yeah.
In the upper right-hand corner of nitrate, what does it have? A -1. This must equal -1. Okay? That's 2 unknowns, 1 equation, can't solve it. What's the 1 extra equation we need? We know that y equals -2. Now what can I do? X plus 3 minus 2 equals -1. I can rearrange all of that and I get x equals
-5. -7. Oh, wait, 5.
lots of little algebra in there. It's okay.
Because you would be -6.
And you add 5 to both sides. Yep. Or add 6 to both sides. And you'd end up with a +5. So what is the oxidation state then for our nitrogen? +5. And this is why students all of a sudden freak out. Because what is the charge on nitrogen? -3. Remember, you went and memorized for nomenclature the charge on a nitrogen atom, right? A charge on a nitrogen atom when? In an ionic compound. Is nitrate an ionic compound? There's no metal. It's not a -3 anymore. We're looking at the bond between a nonmetal and a nonmetal. That's a covalent bond. What is the charge on our nonmetals in a covalent bond? Did you ever have to specify it or use it when doing nomenclature for your nonmetals? No. What changed in the rules? You specified the amount of each of the elements. Okay. Why did we avoid the charge? Because it's not charge. Okay. What we were working with in nomenclature was charge in air quotes. Okay. The air quotes meaning it's not charge. We were actually looking at the oxidation state, but we didn't say oxidation state first because then you start overlapping charge and oxidation state. You have a general idea because you've now had 3 weeks on nomenclature. Since you know charge, we can now add in this extra concept of an oxidation state and then what we can do with it. Is that a hand?
Yes, so oxidation state, does that apply to everything, but it's generally used with covalent bonds?
The oxidation state will apply to everything. Okay? Where it holds its biggest usefulness is in your covalent bonds. Okay? Because that's the only place where we haven't specified charge already. In the ionic bonds, we already have charge established. Okay? So we can just use it straight from that. Okay? What happens in our ionic bonds? The charge on, say, copper in copper nitrate is what? Sure, right there. Just clean all that out of there. What is the charge on the copper in copper nitrate? The charge on copper nitrate is 0. What is the charge on the copper? Okay. This would be going back to that nomenclature system that we had. The charge on our copper comes out to be +2. Why can we solve for a charge there? What kind of compound do we have? An ionic compound. Now we're allowed to use it. Why did we not worry about the oxidation state on the nitrogen in this case?
Because
We can use the charge on the nitrate, okay, which is the sum of the oxidation states of the nitrogen and the oxygen. Okay? So it's stacking inwards. What is it, the Russian stacking dolls? That's effectively what we're looking at in this case. Okay? Which might be a metaphor, I think, if we use the Russian stacking dolls. Okay? So why do we go through and identify the oxidation states? Well, as we saw on the previous slide with the equation, what happened to the calcium? Its oxidation state changed, which meant it gave up electrons. Okay? Something about it changed. Well, where in that equation do you see anything about electrons? What is the symbol for an electron? Negative is its charge. What is the symbol for an electron? E. I see the letter. Do I see the letter E? No. Are electrons in the equation? No. Interesting. Electrons do not show up in the equation, and yet somehow or another, what is calcium doing? It's offloading a bunch of electrons. Where did those electrons go? Something had to explain for that change. Okay? Yeah, we'll just tap through that really quickly. So if we look at another reaction example, okay, because I doubt you memorize things that quickly. Determine the oxidation state for every single element in this question, which means the elements on the reactant side and the elements on the product side. Okay? So try it. If you got a question on where to start, raise your hand. I can come to you, but you actually have all of the basics right now to be able to figure out the oxidation state for each of those elements. We'll take no more than 5 minutes. Probably keep it even lower than that. But he's getting up and writing it down. You for your entire chemistry career. If you move into physics, haunts you through that. Watch out for the minus sign. Okay? It will ruin your life. Okay? So you need to watch out for that minus sign. What happened to the oxygen? Went from a -2 to -2. So what happened to it? Nothing. Cool. Thankfully, I don't have to worry about the oxygen now. What happened to the carbon? It went from a +2 to a +4, so it increased in numbers, so of course it lost. How is an increase equal to a loss? Electrons, which are negatively charged. Okay? Here's where things become fun, because we could look at that and say gaining of electrons or loss of electrons. But if we called it a gaining electron, loss electron reaction, that's too wordy. Okay? We could also say gaining of electrons isn't scientific enough. So what do we do when we have something that doesn't sound scientific enough?
We complicate it.
We make a new word up that sounds sciencey. Yep. What is that new word we're going to use for gaining electrons?
Oxidation.
Remember, we're gaining, right? We're going to call it reduction. Loss of electrons, we're going to call oxidation. Okay? Why? Thank you for asking that. Let's look at the one that lost electrons, oxidation. Okay? Which element lost electrons? Carbon. Carbon lost electrons. Remember, it's here. What happened to the carbon in the course of this reaction? Describe it to me. What does it look like on the left? What does it look like on the right? Well, we don't see any electrons in our equation, so I don't quite accept the reference of electrons. That is true. It has to be doing something with electrons. It looks the same, so CO equals CO? Is that what it shows?
No.
No, what does it say? CO becomes?
CO2.
CO2. What happened to the carbon?
Nothing.
It gained an oxygen. It's not CO, it's CO2. There's a second oxygen molecule. Okay? We increased the number of oxygen bonds, also known as oxidation, because you've increased oxygens. That's the origin of the term oxidation. How about the reduction? What happened to the iodine in the course of the reaction? So we've got a couple options. Number one, we could look at the number of oxygens bound to the iodine. Does it have more or less?
Less.
less electrons, or less oxygens, which means we reduced the amount of oxygens. Reduction. The other option, what is the oxidation state? What happened to it? +5 to a 0, what did it do?
It lost, so
It went smaller, which means it was reduced. Okay? So to decide gaining or losing electrons through an equation, you have to determine the oxidation state for every single element on both sides of the equation. Once you have every single element's oxidation state, you can then compare across the equation, did it change? If it did change, you can then say how it changed. Was it gaining electrons? Was it losing electrons? Okay, but the simple reference of gaining or losing electrons isn't sciencey enough. We add in the extra term. In this case, carbon was oxidized. Okay? I'm referencing what happened to the carbon. And oxidized is an easier verb tense to use than losing electrons. Okay? So you will need to remember that oxidation ties to the loss of electrons. And you will need to remember that the gain of electrons ties to reduction. It might be nice if we had some mnemonic device, I think I actually said that right, to memorize that. Leo happens to be, yeah, that's true. Let's ignore the slide for a moment. Leo is zodiac sign for lions. Leo the lion says grrr. There we go. We've got a mnemonic device that ties the loss of electrons, Leo, to oxidation. Okay. Gain of electrons to reduction. Okay. You still have to go through and solve for the oxidation state to even get to answering this question. Okay. I have noticed that other instructors like other methods for remembering this. Has anyone heard another one from their previous class? No. That's good, because I like Leo says grr. I think this other one's dumb. The other one, oxidation is loss. Loss of what? Electrons. But what's the mnemonic device? Oil rig. Where does it say anything about electrons in oil rig? It's just dumb. Okay. And that was recorded. That's even better. Okay. Most of the faculty here seem to like oil rig. I think it's a waste of time. That's not green enough. That's not healthy enough. Screw oil. Down with oil. Okay. Leo says grr. We can get some, green stuff, life in that. It's cool. That's going to help you then retain the correlation between loss of electrons and oxidation. For those of you that may ask, that's a bit tedious. You will find every single time someone asks me, did this get oxidized or reduced? You will see me mumble sometimes or cover my mouth, because what I'm doing is saying, Leo says Leo lost electrons, oxidation. Oh, I need to find the one that lost electrons. Okay. And for those of you thinking there's no way Mike does that, that is absolutely 100% true. That is what I am processing through because I have a horrible, horrible memory, and I take advantage of the mnemonic device. Okay. Was that cheersing my loss of memory? I appreciate that. Okay.
I think this is a really good example of us trying to overlay systems. We're taking the chemistry content, we're pivoting it into, like, so we tied it to the Aquarius sign or whatever. Is that,
Yeah.
Zodiac
sign.
Sorry, so the zodiac signs. So what you're doing is you're taking your chemistry content, the lost electrons, and shifting it into that new system to make it easier to remember. And I really like that. It sounds very familiar to something we've talked about before.
Lions are kind of cool, pretty animals. We could draw cool, pretty animals and sell those to kids.
Yeah.
Sell them. Okay. For those of you that were like, that was way too easy, and for those of you that thought that was way too hard, tough, we have another definition that we get to throw into this. Okay? Oxidizing agent and reducing agent. Okay? The instant you see ing or agent or ant should be the minute that you probably just walk away from the question and come back later. Okay? Why? What happens with an oxidizing agent? What does that sound like it would do?
It takes away electrons.
Okay. What would happen to an oxidizing agent?
Stole electrons from another compound. reduce itself.
The oxidizing agent was reduced. Yeah, should we say that again? The oxidizing agent, the species that acts as the oxidizing agent, was itself reduced. Okay. What does it mean to be an oxidizing agent? You are causing something else to be oxidized. If something else is oxidized, what had to happen to you? You had to be reduced. You had to gain electrons. Okay? So we are looking very carefully at how we apply those definitions and making sure that we match appropriately. To answer a question about reducing agents, very typically what I would do is cross out reducing agent and I would write oxidized. Next to oxidized, I would write loss of electrons. Then I'd look at my equation to determine the oxidation states and find the one that lost electrons. Okay. These are rather long questions because you have to stepwise through each of those individual definitions and apply them correctly. The instant you start shuffling them, everything goes to pot, and you got to try and start it all over again. Okay? So, we got a bunch of questions up here. So let's go through and work through one of these together, and we'll make one of the other two a quiz on Wednesday. Okay? So, Thursday, whatever the next time we meet is. Let's look at that first equation. Okay. Tin plus 2. What is its oxidation state? Unknown. Thank you for saying unknown. I appreciate that. That beats down in my heart. Why are you saying it's unknown? The oxidation state
Only applies to
you
a
must
compound.
always solve for. How many tins are in that unit? 1. What is the oxidation state? Well, I don't know. I got to solve for it. This must equal what? The overall charge, which is plus 2, because it's written in the upper right-hand corner. When we solve, we find x equals plus 2. We now know the oxidation state for tin plus 2. Why is that interesting? The oxidation state for tin plus 2 also happens to be the charge for tin plus 2. They are not always the same. This is why we have to separate them out. The metals, they will typically be the same. The non-metals is when things go crazy on you. Right? What is the oxidation state for iron plus 3? Well, how many irons are there?
1.
Oxidation state equals, which means x equals plus 3. We have the oxidation state for the iron. Okay. Tin plus 4 on the other side. Yes, go ahead.
Would the aqueous have anything that would change?
Don't worry about the phases yet. Right? Is that getting a bit redundant? Okay. So what would the question be that I could ask here? I could say, well, what was the oxidizing agent for this equation? Okay, well, what did I say? If I ask for oxidizing agent, what should I do? What did I say I would immediately do with that?
Reduce.
I would cross that out and I would write reduced, which then meant gain of electrons. That was just a grr trying to remind you, not like me vocalizing anger with you there. What happened to the tin plus 2? It went from a plus 2 to a plus 4. How does that happen? It lost electrons, right? That was a loss of electrons. Well, what am I looking for? A gain of electrons. So if it's not the tin plus 2, it's the other one. Okay, so let's check the other one. What happened to the iron plus 3? It went to iron plus 2. To do that, what did it have to do? So iron plus 3 gained electrons, which means it was reduced, which means it was the oxidizing agent. What species did it oxidize? The tin plus 2. Okay. Millions of different ways the question get
Speak. Use words.
I'll leave that to Greg. I'll just use symbols. Okay. So here's the next fun question that's going to kind of segue into this. Let's take a closer look at that top equation. Is it balanced? How do we balance? How many tins on the left? How many tins on the right? How many irons on the left? How many irons on the right? Is that equation balanced?
Yes.
So far.
So a lot of people are saying no. Why are we saying no? We have to make sure the electrons balance. How can we tell where our electrons are?
They're oxidation state.
In our oxidation states, which sometimes are explicitly or are never explicitly stated. What is explicitly stated within our equation?
Charge.
The charge. So we can use our charge to indirectly monitor what's happening with our oxidation states. What is the charge on the left-hand side of the equation?
+5.
We have the 2 and the 3, so total charge would be +5. Charge on the right? +6. Is the charge balanced? No. What would we need to do to quickly attempt to balance this? Add what?
1 to the left.
Add one what?
Electron.
Add an electron. Now the question is, where do we add it? So I heard to the left. So if I add an electron over here, what happens to the charge?
Oh, yeah.
It would go to a +4. Am I closer or further?
Right, no, to the right.
I want to add it to the right. Okay. That's our minus sign messing with you. So let's add that electron to the right. What now happens to our charge? Becomes +5. Okay. And we've now, quote unquote, balanced it. And for those of you screaming, no, it's not balanced, you're right. We have an issue with this. Chandler, what's up?
Oh, I was just going to ask if it comes back to the aqueous thing.
Nope.
No.
Don't have to worry about the aqueous.
Okay.
How many times have we seen electrons exist on their own?
Ever.
Never. They never exist on their own. Can this equation work?
No.
We are saying by this equation that an electron is produced and chilling on its own. Electrons cannot exist on their own. This equation is not balanced. Okay? We have to come up with a way to account for balancing the individual elements out so that there are no electrons produced and no electrons consumed overall in the course of the reaction.
So if the charges on each side don't match, they're not balanced.
Yep.
So there's no way to balance.
I didn't say there's no way to balance them.
Okay.
What I said was that it is not balanced. We now know it's not balanced. Okay? We can't just add an electron in because electrons cannot exist on their own. So I can't use it as a reagent or a reactant. I can't create it as a product. So I have to come up with some way where those electrons balance out. Yes.
Are we having charge?
Can anybody? Nope, we aren't changing the charge.
Coefficients on some of the elements?
What happens if we change the coefficients on some of the elements?
Did you say it would equal the same thing?
As long as the coefficient applies to the same thing. It's not going to apply to the same thing. So what do you mean?
So usually the coefficient would only do wouldn't usually the coefficient wouldn't matter if it applies to a compound, but because it's affecting individual elements such as just tin or iron, if we could find a way to balance it.
So let's check that.
When you do it to one side.
I'm just doing it in my head, and I'm not fast. 1, 1, iron, we have 2, 2, charge, what do we have? +8, and +8. Now what do we have?
Balance.
Now we have a balanced equation. Okay. How did I do that? I kind of knew the answer, and I just kind of guessed at it till it worked. We ideally want a method that is not just straight up guessing. Okay, so we'll talk about that in just a second here. Yes?
Another way, the induction of an electron. Or would that not cause?
Don't open that can. Don't open that can. You can talk to me after class if you want to know about that. Okay. So our equation is now balanced. Okay. No electrons are produced. No electrons are consumed. We don't see them show up as a reactant or a product. Our equation is correct. But we now need to know how we got those numbers. Really, I just guessed, and that one happened to work. What if you'd guessed and wrong? Well, you try a different set of numbers. That's not a good process. So what we want to do is separate this equation and hope we can come up with a better way. You can ignore all those answers. Come up with a better way of balancing it. Okay? So let's take a look at this equation. Could we balance this one? How many zincs? 1 and 1. How many hydrogens? 1 and 2. It's not balanced. What do we need to do? Okay. Now my elements are balanced. Can I balance the charge? What happens with the charge? The left, it's... There's a coefficient of 2, so it's a plus 2. Where are you getting a 3 from? On the right, what do we have? A plus 2. Does the charge balance? Yeah. Is this going to be a redox reaction? Yeah. We started with zinc, and we went to zinc plus 2. Its oxidation state definitely changed. But this one was an easy one to balance. Sometimes they're easy, sometimes they aren't. Okay? If we go back to that tin example and try to balance that, it doesn't work for us. Okay? So what we're going to do is come up with a new set of rules. We're going to examine half of the reaction at a time. Well, which half do I want to look at? Just the left? So I'm going to balance tin with iron? Can I balance tin with iron? No. So just looking at the left, well, how about just to the right?
No.
That's still balancing tin with iron. What do I want to balance?
10 and 10.
I will focus on the same element. So I will look at tin, trying to balance with tin. Do the elements balance? Elements being the key word there. I have 1 tin, 1 tin. So the elements balance. Does the charge balance? No. And because I'm now only looking at half of the reaction, I can get away with adding electrons into this. Where do I want to place those electrons?
On the left side.
To the right.
Okay. I'm trying to intentionally pick the wrong one.
What was the question?
Where do we want to place electrons in our equation? And I think the wrong one's on the left. So let's go ahead and add it in there. What happens? What would the charge be on the left?
2 become like 0.
Plus 1 versus plus 4. Did we get closer or further to balancing the charge? We got further. What does that mean?
Wrong side.
The electron was placed on the wrong side. So don't freak out. Just place it on the other side. Try again.
50-50 shot again.
Exactly right. 50-50. But you can check that. So on the left, what do we have? The left is the one when you hold up. On the right? Plus 3. Did we get closer to balancing the charge?
Yes.
Yes. So that's good, but are we balanced?
No.
What do we need to do?
1 electron.
We need another electron. So I could write plus another electron, or
2e.
change the coefficient. Okay. Next equation. I now want to balance the iron with...
I thought electrons can't be left.
I know.
So remember, we said electrons cannot exist by themselves in an equation. We don't have a full equation here, or a full reaction. We have a half reaction. In half a reaction, we're allowed to show electrons because it can't happen on its own.
So we're not
It is happening with its own... Exactly right. It's not going into our overall reaction. It's only going into the
So
half.
we're just adding it separately then.
Yes. We're using the electrons as our charge counter to make sure our charge balances when we run our equation.
So in that case, we can balance any formula pretty much.
Yep. Yep. So look at the next equation. Is that one balanced? What's wrong with it as far as the balancing?
Yeah.
Charge. So for those of you saying yes, you answered the right question at the wrong time. The number of irons, yes, are balanced, but the charge is not. We need to balance the charge. We now need to add an electron. Okay, well, I added it to the right last time, so I must be adding it to the right again, right?
Sure.
What happened to the charge? +1 to +3. Did I get closer or further? Further. I need to put it on the other side. What happens to the charge on the left now? +2 versus +2. Is that half reaction balanced? Yes. Okay. Those are the half reactions. So if I could split this into separate steps, I could then add those two things together and get right back to the overall reaction. Right? Does that make sense?
Not entirely.
I split them apart. If I can split them apart, what could I just as easily do? Put them back together. And how would I put them back together? Everything on the left side is added to itself to be on the left side of the arrow. Everything on the right-hand side added to itself to be on the right-hand side of the arrow. What would we get as an end result? And since I think I've got it nicely written. Okay. Well, this is interesting. Why do I only have electrons showing up on one side of the equation, and why is it not two?
Because there was one on the other side to cancel out.
X plus y equals 4 plus y. What is x?
4.
4. What are you doing? You subtract the same thing from both sides. So we're doing that with our electrons. We can cancel the electrons out on opposite sides of the equation because they did not change. It's just the number. We'd end up with one extra electron left over. Are we allowed to have electrons in our final balanced overall reaction? Mike, Ole.
Oh, I'm sorry. I was trying to figure that out. What did you ask me?
Are we allowed to have electrons in our final balanced reaction? No. What does that mean? This is wrong. Okay? We need to fix it. Okay? We need to fix it in such a way where we don't have any leftover electrons. So what can we do? Whoa, that was not supposed to pop up that fast. What can we do? I can't get rid of electrons here because that's necessarily what's causing that transition. Could I potentially add more electrons here? If I put a 2 here, wouldn't I have leftover electrons? Yeah, so how could I make sure I have 2 electrons here, but without screwing up the charge?
Equal amounts on both sides.
Run that reaction twice.
So you times 2?
I would multiply everything by 2. 2 times 1 becomes 2. What's the coefficient in front of the iron plus 3?
2.
What is it? 1 times 2. Now our 2. And 2. Now what happens when we add the two equations near each other?
2 electrons plus.
The 2 electrons cancel out and disappear from the equation. We just write down the terms that are on the left. Tin plus 2 plus 2 iron plus 3 plus 2 iron plus 2 plus tin plus 4. And if I could rewind, what did we just end with? The answer that I just completely guessed at. Okay. This is exactly how we started this whole process, was balancing that equation. We now have the balanced equation. And we have it without guessing. We have a methodology between how we did it. Step 1. Split into the half reactions. Step 2. Balance the half reactions. Step 3. Balance your electrons to make sure they cancel. Step 4. Add it all up. Okay? The steps are there. It requires practice. To get to this point, what did you need to be able to do? The oxidation states, which is why the video was there and why you were told to watch that. With that,